Hey, welcome to the our session of the Coastal Resilience webinar series. My name is Edwin Espina. I am a fellowship researcher at the UN Decade Collaborative Center for Coastal Resilience here at the University of Bologna, and I am very happy to be your host today. This webinar marks the beginning of a new series that is taking place twice a month on Tuesdays and brings together experts, practitioners, and students committed to strengthening the coastal resilience worldwide. So on today's agenda, we will begin with a brief introduction to set the stage for our today's discussion. Today we have our very first expert, Michiel Knaapen, who will share with us insights on the coastal resilience and environmental modeling. Then we will have space for your questions, so feel free to submit them during the talk. After that, we will have a break to recharge before the second session, and then we will reconvene and introduce our next speaker, Jacopo Alessandri, who will present, and then we will have another opportunity for discussion and engagement. So we're looking forward for a dynamic and insightful session. This series is part of the Coastal Resilience Training course, Co-Growth, which officially started on January 27 and will run until April 11. And this course was designed to equip early career professional scientists and policymakers with the necessary tools to tackle the challenges of coastal resilience sustainability. We are proud again to share that 25 students were selected from over more than 500 applications from all around the world. And this reflects the high level of interest and the importance of this topic. Now the selected students are following a course over 10 weeks that is structured around 5 key modules designed to equip them with a very deep understanding of coastal resilience and the importance for business as well as practical skills for addressing coastal hazards. The course will culminate in a final workshop held in Bertinoro, and all expenses, including travel, accommodation, and tuition, are fully funded for the selected participants. Before we begin, I'd like to take a moment to acknowledge the incredible partnership that has made this webinar series possible. This initiative is made through a collaborative network of institutions committed to advancing coastal resilience, sustainable growth, and climate adaptation. Our key partners include the DCC, which is the Decade Collaborative Center for Coastal Resilience, Deltares, which are experts in water and coastal management solutions, and the CMCC, which is a leading climate research institute, and finally the University of Bologna, which is an academic institution driving research in environmental sciences and sustainability. These organizations are instrumental in shaping the discussions and research that advance coastal resilience. So we encourage all of you to connect with these institutions and explore their initiatives and engage within the broader community of practice to continue this conversation beyond this webinar. Now let's move to our next segment. Today we will have Michiel Knaapen, which he is a principal scientist in Coast and Estuaries Group at HR Wallingford, and he specializes in sediment transport, coastal geomorphology, and data assimilation. With more than 20 years of experience, he focuses on the interaction between engineering projects and coastal protection. He also collaborates with leading universities such as Oxford, Plymouth, and the University of Twente, and serves as a reviewer for several scientific journals. Now, some quick notes about the Q&A session. Each of our speakers will present their insights, and we will follow with your questions. So feel free to submit in the Q&A section, and we will address as many as possible. Finally, note that this webinar is being recorded, and it will be made available for educational and promotional purposes. So by participating, you consent to this recording. So without any further ado, Michiel, the floor is yours.
Thank you very much, Edwin. Let's start with sharing my screen. Okay, can you see my screen?
Yes, we can see it.
Okay. So as Edwin said, my name is Michiel Knaapen. I work at HR Wallingford as a scientist in coastal sand transport, mostly nowadays. I've been at HR Wallingford for almost 18 years now, and 5 of those years I predominantly worked on this project from 2019 to 2024, building the information on the Texas coasts and the sediment budgets that are relevant there. But and the context of the work is that Texas, like all other regions on the coastline, is struggling with sea level rise related coastal erosion. So the whole of the Texas coast is under is property of the Texas General Land Office. So they are the institute that is responsible for coastal protection. They're not responsible for flood protection, which is the U.S. Army Corps of Engineers. But anything coastal erosion related is the merit of the Texas General Land Office. They're seeing a lot of erosion. The plot shows the retreat of the shoreline in feet. Sorry that the color scale is missing, but on average it's about 4 meters a year coastal retreat. But it's varies along the shoreline, and not completely surprising. Most of the erosion happens close to river exits, where also most of the development is. So there's a spot there, there's a spot in the far northeast and the far south. So I said on average 4.1 meter per year, but some areas lose about 30 feet per year, so 10 meters a year. And a lot of the erosion is happening in valuable land areas. But there's also large areas where it's a more or less undisturbed beach with what they call the dune system behind it, but the dunes rarely get above my height which is 6 foot or 1.8 meters. So to sink more and more erosion, they need solutions. Hard structures don't work, are costly, are ugly, and cause problems elsewhere. So increasingly, the General Land Office is looking at soft solutions, which for uninterrupted sandy beaches basically boils down to nourishing with sediment from that was acquired somewhere else. But the need for sources is increasing. There aren't that many sources, and there have been a few sand nourishments where they place sand on the beach, and the sediment disappeared as quickly as one wouldn't dare to imagine. So in one instance, the whole nourishment was disappeared after the first major storm. I don't know the precise background, but I saw that there was a varying range of backgrounds. So I'm starting with a quick coastal processes 101. How is sediment moved along the beach? If you've got a nice long beach and you've got the sea where waves are coming in, they rarely come in straight at the beach. Usually there is an angle between the beach and the crest of the waves. And that means that sediment starts moving. The most basic way of transport is that sand grains move up and down the beach with the water of the waves. When the waves run up to the beach, they take sediment up the beach, and then when the water retreats, it goes down again. So if you look at a single wave event, you will see the sediment moving up and down and not much else. But if you would be able to track a single grain and look over a large number of waves, hundreds, thousands of waves, you would start to notice that not only it's going up and down, but gradually it's moving along the beach as well, which is a process we call littoral drifts. So you get that up and down movement, and gradually sand moves in the direction that the waves are pushing it. If the waves turn the other way, then the sand would move the other way again. On top of that, there is the fact, is the fact that the angle between the waves and the beach leads to water level difference, and because of that water level difference, the waves start creating a current along the shore, which we call a longshore current, very imaginary. So the wave pushes water in that direction, and the water escapes basically by going along the beach. And you get kind of elliptical shaped current along the shore. And that then is often enhanced or reduced by tidal currents. So based on this principle, there have been a lot of studies in the past, but not that many studies for Texas. But whatever study was done was using this principle, and the results show that there's a clear pathway of sediment over the years from east to west up to roughly the 27th latitude north, and northwards south of that latitude. The other information that we have is that there are very limited sand deposits in the area that are useful for nourishment or suppletion of the beach sands. Red shows all the surface areas that are covered by sand. Quite a few are just too far away to be commercially relevant. There are a few that are on high sandbanks. If you start fetching those, you expose the coastline to too much energy and start eroding. So in reality, there are a few small areas that could be used to find sand, which they're just too small to be a source for the whole of the beachfront. So the general land office realized they have to be smart, they have to be efficient, and they were having problems. Can you still hear me again?
Yes.
I got muted for some reason. The aim of the project is to explain why those unexpected changes were happening around nourishment and identify potential sinks and sources.
Michiel, are you able to share again? It's stop it sharing. All right, thank you.
Okay, so to give you an idea about the size, showing the whole of the Gulf of Mexico, and this section is the whole area that we were investigating. We did that sediment transport modeling with the Telemac suite of OpenTelemac, where we couple wave currents and sediment transports. The area was just too big to do in one go, so we split it up in 4 regions. Region 1, 2, 3 is green, and 4 is yellow, to make modeling feasible, but also to be more effective and efficient in the data gathering and data processing. We started off with region 1 because that's economically the most interesting area. It's near Houston over there, and most of that coast is developed or has villages on it. The next step was region 4 because of the importance of a port in that area. And only in the later stages we did more undisturbed areas. I'm going to talk about region 4 because, as an example, how we did the modeling, because scientifically that was the most interesting part, because there were some interesting findings that then explained what we found in other regions as well. Quickly go through it, we're not modelers, so but to give you backline, This is a sediment mesh of 500,000 nodes with about a resolution of 10 meters at the breaker line and 5 kilometers offshore. You can see some barrier islands along the shore, which are part of the model and can be eroded, and sediment can deposit on it. We use open source global models to drive our modeling with water levels and currents at the boundaries, waves coming in at the boundary, and atmospheric pressures and winds. And then we spend a lot of time figuring out which period was the most representative for the last 30 years. And if you looked at all areas together, then 2018 was the best. It also had the benefit of not having a large hurricane in the year, which meant that a very unpredictable cause of sediment transport doesn't change the results too much. Otherwise, we kept the modeling as much as possible as we could to default settings, which were originally used for a site in the UK. So the model settings for the UK model were almost identical as the ones here. For the flows, the only real change compared to the previous UK model is that we created a spatial friction map. So there's different frictions in the muddy lagoons than in the silty oceans, and the beach and inlets are different again. So when we run that model, no, I can't undo my, no. There we are. I've got you're now seeing a video of the waves on the left, the currents on the right, and initially it's just ocean currents going around, and then you see the wave speed pick up. And if you look careful around the coastline, you can see, you could see a current picking up, driven by the waves. I'll start it again. Just before the storm picks up, you can see a current along the shore that gets stronger when the waves get stronger, and then when the waves disappear, that current disappears as well. Sediment, again, very of its default settings. The only change is that we create a sediment map where, based on the sediment samples that were available, we decided what the size of the grains is in those areas. Offshore, it's silty. We didn't have any data there, but we left that silty to make sure that there's as little an edge to the measured data as possible, and then closer to the shore, it gets coarser. And the beaches itself consist of fine sand. That was modeled with 5 classes, so we could model both sand movement and silt movements. We had some data to validate a model, but given that the model is about 200 kilometers along the shore, and we had current measurements in 5 locations, water levels in 3, and 2 wave points. That's not very much for the size of the area, but that's the best. That's the only thing we had available, so we had to do it, what we had. But the comparisons were quite good. This shows the wave height near the shore. So at the location right there, and the direction of that the waves are coming from. And the match was surprisingly good given the size of the model domain we're working with, and given that we're trying to model a whole year. This shows about 30 days of data, but we had much more than this. If you look at statistics, for those who are interested in it, root mean square errors were order 0.3 meters in water levels, velocities 0.1 meter per second, and wave heights varied a bit along the sides. But closer to the shore, we were doing better than offshore, surprisingly. And the skill score varied from sufficient for velocities offshore, where the velocities are low, which are always difficult to predict, to good and very good closer to the shore. For sediment transport, we didn't have direct sediment transport measurements. We did have 2 navigation channels that are being monitored and dredged, so we could see if our model could predict the bed level changes in those channels. And based on that, we assumed that the model was doing what it should be doing. On the bottom, we can see the measured bathymetry at the Bologna-Santiago Pass, with red being the deposition. So on the northern edge of the channel, there was deposition. And the model predicts a very similar pattern, not the noisy data elsewhere, but that key element was predicted really well. If we then look at volumes for Bologna-Santiago Pass, the difference between measured and model infill was 6%, which must be a coincidence. It's never this good. So, but yeah, we're very happy with that comparison. For Mansfield Pass, which is much more a natural changing channel because it hadn't been dredged in the years before 2018 for quite a while. And there we're getting at least the correct effect, as in that in 2018 it was eroding rather than infilling, but there was about 50% difference, which for bed level changes usually is more realistic error. Usually in sediment transport, we are happy with a factor of 2, so 50% isn't too bad. But the important is where we have got a very clear force system. We know exactly what's happening. We also compared it with long-term dredging records. For Bologna-Santiago, it now becomes a bit more realistic with 20 to 30% difference between our representative year and the last 20 years of channel sedimentation. The other data that we did have, and that came in once we'd completed our modeling, so it wasn't really a calibration tool, but it did give some very good verification. Thickness and all did a tracer study by placing a lot of fluorescent particles on the bed in the green box where my cursor is now, which is within dredge spoil placement sites. And then they started taking sediment samples for the year after the placement to see how many of the fluorescent particles they could find back. And this was the result after a month. The red box is now the placement sites. The dots are all the sample sites, and the color of the dots tells us how much of the samples were, how many of the grains were fluorescent. The highest was still in the area of the placement, but they found a two-way system in that offshore the particles are being displaced to the south. On the onshore part, they moved to the north, which is exactly what our model was showing. So finally, that's the confirmation that our modeling was doing what it should be doing and predicting the right things, which is important. We then created these kind of maps showing the vectors showing direction. The color scale shows the amount of transport from none in blues to lights and blacks, where blacks give the highest transport rates. If we look at the inset near the shoreline, there's a split system with southward transport on the offshore side, and only in a narrow band near the beach, the sediment transport is to the north. Which, if we integrated over the profiles, meant that the residual transport direction is opposite of what previous was assumed. And the reason for that was, trying to go back. Just let me. The reason for that is the littoral drift, that wave-driven transport is still to the north, as the common knowledge understood. But the interaction between the ocean currents in the area and the longshore currents during storm waves, which have a dominance from a different direction during winter, you get this effect that the littoral drift is to the north, but overall the transport is to the south. There was so that's why we're getting this difference. There also was a clear seasonal effect. So in summer, the transport is doing according to common knowledge. So even people who went out in the field usually did do that in summer, because that's when the weather's better, that's when it's safe to go on the beach, etc. And they got confirmation that yes, the little drift, the sediment transport along the shore is to the north. But in winter, the system changes. The ocean currents are driven by stronger winds, creating counterclockwise circulation along the shores, along the Texas coast, driving sediment to the south. And those transport rates are a bit stronger and more spread than the northward. So overall, you get the northward effects. And our conclusion for this area, therefore, was that you need to take your ocean current into account for this area. if you want to know where the long-term transport pathways are going. I'll quickly. And that then leads to some important information for coastal management. We're now in the phase of creating GIS. I'm not involved in that anymore. I'm not a GIS specialist. Struggle enough to make the pictures using GIS. But colleagues are working on it to create an open access GIS together with the GLO. And that will have static layers where per section of the coastline will have information on the grain sizes, on the sediment fractions in it, but we'll also create, sorry, why is it doing that? There's we'll be putting on, that's not helping, profiles. It's going through it automatically. I'm very sorry. Profiles that show the transport rates for every year and every month. We'll have the resulting longshore transport rates. Not sure why it's happening, but seems to be automatically scrolling forward, so it shouldn't be doing. So the transport rate as factors. We'll have nearshore transport factors. We have offshore transport factors. We have factors through the inlets, and we have onshore, offshore transport along the offshore ends of our cells, which basically forms the sediment budget. Based on those transport factors, you then can determine which cells will be accreting, which will be eroding, and at what rates. As I said, the results had some implications for the coastal zone management. So our clients, the General Land Office, the GLO was very happy with our work. Regarding the beach nourishment disappeared, it was nourishment. I don't know what I've done to make it skip through, but I'm gonna try jump out of the presentation mode, so it will be a bit smaller, but
I believe that we could go on and wrap up.
Okay.
We have already reached the time for your presentation, Michiel.
Oh yeah, sorry. Am I still sharing or? But anyway,
Yeah.
can you see it? Or?
Yes, we're able to see.
I'll quickly wrap this up then. The nourishment was here, or roughly at this location in this plot. The column of knowledge would go south. If you look at the profile, if you average over the profile, that is the direction that sediment is moving. But because of this near shore band where the sediment is moving the other way, the sediment that was placed near the shore was rapidly moved north to the breakwater. The breakwater caused it to go offshore and it disappeared in a single storm. And similarly, there's the problem that there's a placement site north of the Plaza Santiago's channel that I talked about earlier. If you place sediment there, the ocean currents will push the sediment in the channel. So it's very wise not to use that placement site anymore. Right. Lots of implications, lots of conclusions. But I hope I've given you some flavor of this project and the complications that can occur in what's initially looks like a fairly simple, easy to understand beach system. Time for questions.
Okay, thank you very much, Michiel, for this insightful presentation. Opening the floor for questions. I have some questions in the chat. Kadir asks, is there a particular reason for choosing Telemac for the models? Does it perform better modeling morphodynamics in large domains in comparison to modeling suites like Delft 3D? And was morphological acceleration considered for long-term forecasting, or do you find it too uncertain?
Good question. Thank you very much, Kadir. Telemac is very similar to Delft 3D. There were three reasons why we use Telemac. As an institute, we are familiar with Telemac and feel much more comfortable with Telemac than with Delft 3D. That's in itself a good reason to stick with what you know. But also at the time we started, the flexible mesh in Delft 3D was, how would I put this, not completely developed in the open source version. So there were some issues with flexible meshes, and for a model this size and the resolution we needed on the shoreline, you do need a flexible mesh instead of a structured grids. And the third reason was that Telemac is very efficient in to use in HPC with domain decompositions and multi-processor runs, and that was just crucial. Morphological acceleration, we did consider it previously, but we found that in the near shore, it just creates errors too quickly. If you're interested in offshore, in slightly deeper water, it can work if you don't make your speed up too long. But near the shoreline, you just create artificial errors that are not real. And before you know it, you're looking at something that's not realistic anymore. If you work hard, you and then compensate those artifacts with specific model settings, but that beats the point of understanding what the system is doing. And on top of that, the interest here was more in the sediment pathways. Where's the sediment going? How is it moving? Than in the morphological change. The client knows pretty well where the beach is eroding and where it isn't.
Thank you very much. I also open the floor for questions. You can ask them directly or post it on the chat. For now, I have another question on the chat from Priscilla Nada, who asks, were there already existing coastal protection structures in the area? Why was sand engine or beach nourishment in the suitable measure?
Let's see, how can I explain that best? So there are a couple of there. If I zoom out a bit, you can see where I am. We're Houston. Offshore of Houston is Galveston, where basically there's a small town, basically on the shoreline. So there's a seawall there, and there are some groins. But the GLO was seeing that more and more there are issues related to those structures. There's a seawall that protects against flooding, and west of that seawall, there's increased erosion. There's a bit of, there it is, a clear cutback of sediment, and where the beaches are protected by groins, you basically see the same effect. It keeps the sediment on one side, but as a result, you get erosion further down. So hard structures can keep sand on a particular area, but it will mean that area downdrift further downstream of the transport, you get more problems. And independent of which structure you take, whether it's longshore groin or it's offshore breakwaters, if you interrupt the sediment, the littoral drift, the longshore sediment transport, you take sand away from an area elsewhere. So basically, they realized that they were moving the problems rather than solving them. So that's why they decided that nourishments are the suitable measure. I hope that answers the question.
Okay, thank you very much. So I open the floor if there are any more questions. Okay, we have one last question from Kaina. How do you identify new sources for sediment nourishment?
One of the conclusions was that there really is very little, confirming what they know from surveys, there's very little sand deposits available. But we have identified a few inlets where sand is moving into the barrier systems. Trying to see, yeah, here's one. Don't know why I stopped sharing, but so there are several of those small inlets, and a few of them have flood delta, so a fairly large deposit of sand on the inside of the barrier islands. And a few of them are growing, and our modeling showed that sediment was moving towards it, which would then be a good reason to take that sand and put it back on the beach. So that's basically the only sediment source that we could find is what is the natural sediment sinks in the inlets. But even there are very few of them. because most inlands are exporting sediment. So in general, yeah, if you know where the sand is going and it is not going elsewhere, if it's going to an area that's not relevant to you, and it's not moving to relevant areas for you further on, then you could dredge those areas and place that material where you want it.
Okay, thank you very much. And thank you all for your questions. And a big thank you to Michiel Knaapen for such an engaging presentation. Now we are having a break and we will come back at 10 minutes. Thank you very much. Hello and welcome back. I hope you all had a chance to take a short break and recharge. And now we're ready to continue with the second part of our webinar. Here's a quick overview of the second part of our agenda today. We will have an introduction and we will introduce our next speaker, Jacopo Alessandri. Jacopo Alessandri will present from 1520 to 1550, and then we will have finally another opportunity for discussion and engagement through our Q&A session. So we look forward to a dynamic and insightful session. So let's get started. So, Mr. Jacopo Alessandri, just a quick presentation. Sorry. He holds a bachelor's degree in atmospheric physics and meteorology and a master's degree in physics of the Earth system from the University of Bologna. And in 2022, he earned a PhD in geophysics from the same university with thesis work on coastal modeling studies for forecasting and remediation solutions. His research focuses on coastal processes, including lagoon dynamics, coastal ensemble forecasting, and the evaluation for nature-based solutions like seagrass for coastal protection. He is currently working on numerical models to explore the interactions between physical and biogeochemical variables in coastal environments. He has collaborated with institutions as ARPAE and the CMCC in European and interregional projects. Now, Jacopo will present his insights and then we will follow with a Q&A session. Please feel free to submit your questions in the Q&A section and we will address as many as possible. Finally, please note that this webinar is being recorded but it will be made available for educational and promotional purposes. By participating, you consent to this recording. And without any further ado, Jacopo, the floor is yours.
Thank you, Edwin, for the nice presentation. I'm trying to share the screen. So, voila. Share. Now. I swap. So you should be able to see my presentation.
Yes, we can see it. Thank you very much.
Perfect. Okay. So welcome everybody. I'm Jacopo Alessandri, now working in University of Bologna as a research fellow. I will speak about the assessment here of nature-based solution with digital twin of the ocean. But let's start from coastal environments and what are the hazard related. So there are many ways to classify coastal environments. One can classify with based on marine habitats or the kind of beach. So I will be very simply do these classifications. So we have like kind of rocky shores with fjords, high cliffs, going very deep, usually very fast. Then we have sandy beaches with dunes and usually flat coastal areas, and wetlands with mangroves, lagoons, and estuaries, usually called transitional environments. And then all these environments are strictly interconnected, because we can have also sandy beaches in wetlands and rocky areas in sandy beaches. And also we can find seagrass in all these kinds of environments. Another very important things is that all these environments are interconnected and highly urbanized, because we can find human infrastructures in all coastal areas, from small villages to mega cities. And so coastal areas are very important. First, they have high biodiversity, biological productivity, and population growth and economic activity focus in coastal areas. So just few info. 40% of world population lies within 100 kilometers from the coast. And also the largest mega cities are in coastal areas. And also the economic activity and the population growth will be occurring in coastal areas in the next decades. So we have to deal with coastal hazard. Let's talk about some what is coastal hazard. Well, erosion, coastal retreat, storm surge, and coastal flooding is for sure is the focus of this presentation. But there are many other coastal hazards that are interconnected, like sea level rise due to melting ice, saltwater intrusions that has very bad impact on agriculture, coastal pollution, and marine heat waves, like also many other related problems. But today we will focus on storm surge and coastal flooding, basically. So, what is the effect of climate change on coastal hazard? In this picture, you see that a lot of points from green to red, these are urban population. And inside the dashed black line, there are areas that are expected to have a diminishing coastal resilience in 2050. Why? Because coastal environments are hotspots that are threatened by climate change due to the warming of the atmosphere and the ocean, sea level rise, the intensification of tropical cyclones, and extreme events in general. So, storm surge, what is it? Usually is a combination of high tides and severe wave conditions, high winds that combines and severely erode beaches. So 1.5 million people are affected annually by storm surge, and 40% of these major events occur in South and Southeast Asia. So it's very important to deal with coastal hazard and to plan future strategy of coastal management with the development of early warning systems and trying to find innovative solutions that are sustainable and that can lead to a resilient coast. Like, for instance, nature-based solution, that is one of the topics of today. But what are nature-based solutions? There are a few definitions of that. I choose this one, action. So nature-based solutions are action to protect, sustainably manage, restore natural and modified ecosystem that address societal challenges effectively and adaptively, simultaneously providing human well-being and biodiversity benefits. So we can have 5 key points for nature-based solutions. So they have to address specific societal challenges, benefits. They have to be There should be benefits for biodiversity, benefits for human societies. They have to be multifunctional, and there should be a stakeholders involvement. But how these apply to storm surge and coastal flooding hazard? Okay, let's see what is the spectrum of coastal protection. We can have a gray to green spectrum from the gray solutions, so-called gray solution, like seawalls, groins, and breakwaters. Then what we can call hybrid solutions, so living shorelines that are a mix of natural environment with some engineered coast, beach nourishment, that are very useful, but unfortunately don't act on the causes of the erosion and the restorations. And then what we can call green solutions that are the nature-based solutions. So the restoration of mangroves forest, of seagrass meadows, and also coral reef and oyster reef. But today we will focus on seagrass. So the seagrass is, well, there's a global distribution on seagrass, except in the Arctic and Antarctic region. We have seagrass all around the world, with different species that populate different, I can try to use a laser point. Different species that populate different areas of the world, like in Mediterranean Sea, we have a lot of Posidonia oceanica and Zostera marina, as well as in Baltic Sea. And so this seagrass is a group of marine angiosperm that adapted to life in the coastal zone. And they provide ecosystem services that support both the environment, biodiversity, and human well-being. Unfortunately, the seagrass is experiencing a decline due to climate change and also a lot of human-induced stressors. So the important ecosystem services are listed here. So they provide coastal protection, stabilizing the sediment, and removing energy from the wave and flow fields. They sequestrate carbon because they use carbon dioxide for photosynthesis. They support biodiversity and providing a nursery ground for fish and other marine invertebrates. And they improve water quality because filter pollutants and enhance water clarity because of sediment stabilization. But how can we assess the coastal hazard reduction provided by seagrass? We want to try to do it with a digital twin of the ocean. But first, I want to tell you what is a digital twin. So also here, there are a few definitions, and because it's a very recent concept. But basically, it's a virtual replica of a real system or process that allows simulation, predictions, and of the behavior of the system, combining also ocean observations, advanced modeling, and artificial intelligence. And how this applies to the studying of the ocean? Well, the technological development now is allow us to have ocean models that can reproduce very well realistic structures in the oceans. And so we can design with them solutions for coastal hazard reductions. Like the project I'm involved now on this is the Edito Model Lab that try to make together observations and modeling to build a digital twin of the ocean in European Union. So now we tried to take a look on how to build a digital twin of the ocean for the assessment of the seagrass as a nature-based solution. We basically do it using two models, one ocean model and one wave model that I will briefly present. So the Scheifele MPI is a finite element model that solves the primitive equation for the oceans, so the ocean circulations. It uses an unstructured grid that is very useful because we can describe also very peculiar morphology in coastal areas. Like here on the right, I have an example of a domain in northern Italy with lagoons, and we build this grid, also enhancing all the details of the lagoon that we want to study. So it's very useful. Here we have some. It's very useful to build starting building a digital twin. We have here some example, some details of the numerics that are used by the model. Like being a 3D model, we need the turbulence model. The horizontal viscosity is described by Smagorinsky formulations, etc. And here are some applications that used by Scheifele, like it is used for operational activity, like the other test system, or in this case, the seagrass module is integrated in the model and used for the MBS assessment. Is coupled with a sediment transport models, and also the wave modeling is the coupling with a wave modeling is ongoing with WaveWatch 3. That is the next model I present. This is a third generation wave models, so solving the spectral action density balance equations. And it can use also an unstructured grid, and it is used for operational activity also, nature-based solutions, so coupling with currents to study, for instance, the effects of medicane in the Mediterranean area, and also for global application for the study of the effects of hurricanes. Here I have some details on how we add seagrass in the model, in these models. So here on the bottom left, we have some details on how the seagrass, what are the seagrass effects on the flow. So we have that when we have seagrass, a submerged canopy layer, turbulence is mainly generated at the top of the canopy. So we have a reduction of the velocity in the seagrass meadows, and then we have the generation of this shear layer with a lot of turbulence here. And also in the 3D models, we need to account for this small turbulence that we had to add in the turbulence equations. And then other important things we needed to add is the flexibility, because seagrass flex due to his buoyancy, his rigidity, and due to the currents. And so the rigidity, the seagrass change his length with the current velocity and other physical characteristics. So we try to verify the goodness of the parameterization, reproducing the results of the study of Infantes et al. 2012, where he has measurements of significant wave height in areas without seagrass offshore, and area with seagrass inshore. And so we verified that an experiment without seagrass can reproduce very well or fairly well the significant wave height in the offshore area, that is the blue line, with no vegetation. Then if we add vegetation with no flexibility, we obtain the red curve. That is, it is reducing the wave energy too much, because we need to compare it with the solid gray line. That is the measurement of significant wave height where we have seagrass. While if we add the flexibility of seagrass, we can obtain fairly good results of the significant wave height. And so next step was to apply the digital twin to our real coastal settings. So we choose 3 areas around the Italian peninsula. One is the Venice Lagoon, Civitavecchia in Tyrrhenian Sea, and Emilia-Romagna in the Northern Adriatic Sea. So where available, we use the data of seagrass distribution, like here in Venice and here in Civitavecchia, where we have different kind of seagrass. For instance, in Venice we have Dostera marina, while in Civitavecchia we have Posidonia oceanica. But also we use for instance, in this area, in Emilia-Romagna, we don't have actually seagrass in this area, but we want to see the effects, potential effect of coastal altar reduction if there will be some seagrass there. So a what-if scenario. So as I already mentioned, we used this seagrass distribution maps were available, so observations, and also the seagrass physical characteristic needed for the model were available. And then we set up simulations using ECMWF analysis as meteorological forcing, and Copernicus data as open and initial conditions, bathymetry for EMODNet. For the ocean circulation, we also need to add the rivers inflow taken from observation where available, and climatology. And then we did different simulations with different period for each of the domain. One with a reference that we can call reference simulation with no seagrass, and another with simulation with seagrass, to compare the two simulations. So we validate the control simulations, and using the data of significant wave height, and or also salinity temperature for the ocean circulation model, and sea level, just to validate our models. And then we can take a look at what are the results of these simulations. So as I already mentioned, we did the comparison between the simulation with seagrass and the one without seagrass to evaluate the impact of seagrass. Here we have the sea level. And for instance, if we have in Emilia-Romagna, where we have an open coastal areas, the effects on sea level is to increase upstream the seagrass patch and decrease downstream the seagrass patch. However, this in open coastal areas like this is very, very is negligible, because we have here around 1 millimeters. While it was interesting to see that in lagoons, or like here in Venice Lagoon, where we have seagrass inside the lagoon, we have an increase of sea level in the inlets, while the sea level decrease inside the lagoons up to 5 to 10%. That is not negligible. These are the effects on current velocity that can, so the seagrass dissipate the flow energy and can reduce the velocity amplitude up to 50 to 60% in the bottom layers. As we can see here for the Venice Lagoon, where we have patterns of decreasing velocity, but that also of increasing velocity in some other areas. While in Civitavecchia, that is a more open coastal area, we have a decrease of the velocity in the bottom layers, and also the same in Emilia-Romagna. And it's interesting to see how, due to turbulent effect, we have also a decreasing of the velocity all along the column water. And then also the most important effects is in the decreasing of the significant wave height. Because in all the settings we tested, we have a dampening of the wave energy between 10 and 15%. And this is we consider it a good results, and to obtain these results was essential to add the seagrass flexibilities in this simulation, because otherwise we reach values of dampening that was too much, like between 40 and 80%. And then we go further in the DTO implementations, trying to study the effects of seasonal variability in seagrass. Like we had observation in Civitavecchia of different substrates and on the leaf length of a seagrass in the different substrates. As substrates, I consider rocky substrates, sandy substrate, and degrademate. That is a substrate made by death seagrass. And then based on the observations of the leaf lengths in different seasons and for different substrate, we build a model of seasonal variability of leaf lengths. And then we add these informations to the DTO to obtain, and this is the results. So it's the wave dampening in different seasons. And as you can see, in summer, we have a larger dampening of the wave energy because, let's go here. As you can see, in summer, we have a longer leaf length. Then the bad weather come, and most of the leaves are ruined by the bad weather and storms, and so the leaf length, the mean leaf length decrease. And this for sure has an effect in the dampening of the energy. And we can see clearly here what is the effect on of the seasonal variability. Because, for instance, we have the significant wave height variation of an experiment that use the seasonal variability of seagrass against one that has a fixed leaf length. And we can see that when we have, in winter, we can have an increase of 10% of the significant wave height because we have shorter leaf lengths. And it's also changing among the different substrates. While on the opposite, we have an amplification of the wave dampening, so less significant wave height, a reduced significant wave height during summer, where we have a longer leaf length. And the same could be said for the orbital, bottom orbital velocity. Okay, so I'm at the end of my presentations. So the DTO, build a DTO is a step-by-step process because we started from numerical modeling, so with that can describe coastal areas in really good details, and then try to add all the observations that we have to integrate the DTO and to have the most reliable digital twin of the ocean, with the aim, in this case, of having an assessment of the seagrass effectiveness as a nature-based solution. So for sure, in the future, will become an essential part of the development of the DTO to integrate artificial intelligence tools into numerical models and observations. And also, like indeed the model development has to continue, like to add new processes, like was done for account for seasonal variability of seagrass leaves length, and also to couple models, like in what I show you, the ocean currents and the wave model were uncoupled. But having a coupled model will increase even more the reliability of the digital twin. And at the same time, observations are also fundamental, both for as input for data and for validations and calibration of the DTO. So that's all. Thank you. And I'm open to questions.
Thank you very much, Jacopo, for your insightful presentation. We open the floor for questions. So if you have any questions, please use the chat function. Our first question is from Kadir Orhan, who asks, is seagrass parameterization based on physical modeling or mathematical assumptions?
Okay, well, here is so let's come back here. Okay, so this is based, the seagrass implementation is based on these equations. That is a common drag equations that is used in many models. And it's not specific for seagrass. This is just for any object we can have that generates a drag in the water. Then we used to substitute some of the key parameters with parameters that are relevant for seagrass, like the seagrass stem diameter, the seagrass density, and well, the drag coefficient is something that has to be tuned. Also, if it can be based on physical assumption. And so see, yes, basically it is based on physical models. Yeah. I don't know if I answer the questions completely.
Okay, thank you very much. We also welcome for questions. If you like, you can open your microphone and ask your questions directly.
Okay.
We have a question from Kaina. What are the different types of seagrass restoration? No. What types of seagrass restoration have you identified during your project?
Types of seagrass restoration have you identified during your... Well, I'm not an expert of seagrass restorations, but what I know is that the work I show you here different test case, and what I can tell you is that here in Civitavecchia, this work was started because there are projects of seagrass restorations, and but unfortunately I can't help you in in telling you what are the types of seagrass restorations, because I'm not it's not my expertise there. I'm sorry.
Okay.
Thank you very much. We have another question from Isa Hamid. Are there any sensors for the detections of seagrass particularly?
Well, there are some people that is developing some instruments to map the seagrass. For instance, in CMCC, they are working. It's in the conclusion, not very, but this is a drone that people in CMCC in Civitavecchia is working on, and they try to use it and to adapt it to also let it useful for seagrass measurements, like the leaf length, and also to try to quantify the density per meter square of seagrass. And otherwise, yeah, as there are the common ways that is a diver going down and take measurements. But yes, there are new development in the seagrass measurements.
Thank you very much. We have another question from Isadora Kimbo. Are you aware of other projects similar to this one that focus on mangrove ecosystems?
Well, if I go in Nardar, there is another question before by Isa Hamid. Your study areas are tagged as lagoons. What are the situations for hazards at seas, ocean areas? Well, I think you are talking about the area I show you here, but basically, well, the Venice Lagoon, since all the area between, like in this area I'm showing you with the laser point, this is the Po Valley, is a valley of the Po River. So being a river plain, it is subjected to subduction, and so it is affected by storm surge and coastal flooding. Now, in Venice, this was a big problem, but now they have the Mose, that is this system that closes the inlet when there is very high water, and so this is hoping it will work for. We hope it will work for a long time, but now it's not anymore a big problem due to this in the high water level in Venice Lagoon. And while in other areas, like here, that there's open coast, there are usually one or two per year, a combination of events that bring very high water level here with storm surge and problems of coastal erosion. And the same in Civitavecchia when there are strong winds from south and southwest direction. So basically, these are the hazards related to these areas.
Okay, thank you very much. Now we go to our next question from Isadora Timbo. Are you aware of other projects similar to this one that focus on mangrove ecosystem?
Okay, well, no, unfortunately, I'm not aware, but for sure, I know that in Delft, in Deltares, they are really involved with also study the mangroves effects, and I know that they have they have a project somewhere. I don't know exactly where, but when I visited, they are building. They have like a greenhouse with mangroves to test the effects of mangroves, and they have a large experimental a large experimental tank where they do these kind of experiments. And they are for sure involved in some projects, but I don't know where.
Okay, thank you very much. And then we have another question from Chipo Patel. Are there any other solutions to counter waves due to shorter length of the seagrass?
The solution to counter waves. I can't really understand the questions. Due to shorter length of seagrass, well, so I think you mean if there's other solutions, because short seagrass is not very effective. Well, I don't know this, but for sure there are some limitation in the seagrass effect, because maybe I forgot to put here in the presentation, but for sure the seagrass, the main problem of seagrass is that when there are very large storm, it can be buried and then die, and it becomes useless, or it can be eradicated and then it becomes useless again. So we need to, especially if there are restoration problems, to account for the areas where this restoration is done, because if they are very exposed, you need or one to do a very big transplantations, such big that you like pass like a threshold of a critical mass of seagrass. That means that it can resist also to like storm effects. Otherwise, it becomes useless. So I don't know if I answered this question, but at least I added this detail that maybe was missing in my presentation. It was important.
Yes, I believe that the question was oriented that if seagrass, due to their short length, are effective to attenuate wave energy. So among these natural-based solutions, there are also the seagrass can also complement with other types of vegetation, such as mangrove or salt marsh restoration, as well as coral reefs in the areas where they are located. And I believe that they also can be complemented with engineered solutions or great solutions as well, right? As well as sediment management.
Well, seems I answered the question. Okay. So next question: can this model be applicable in a sand engine project? Well, sand engine project. Unfortunately, I'm not really aware of what a sand engine project is.
I believe it refers to beach nourishment, perhaps.
Ah, okay. Well, okay. Well, the problem is always the same. If the nourishment become a problem for seagrass, like that it become buried by sand, the seagrass become useless. So it has to be one should think a lot when doing this beach nourishment in areas where there is an ecosystem that can be altered by nourishment. Yeah.
Cecilia.
Okay, thank you very much. Then we have another question from Isa Hamid. Two suggestions were provided under the nature-based solutions. Are there more?
Sorry, two suggestions were provided
under the nature-based solutions. Are there more?
Well, nature-based solutions. So you mean like suggestions? You mean that here I talk about mangroves restorations, oyster and coral reef, and seagrass restorations. Well, if there are more, for sure there are more. I think that there are more than what I can also know. But everything that can enhance the natural environment and together being provide an ecosystem services that help the society can be considered a nature-based solution, actually. So I don't think to have more suggestion about this, but having in mind the definition of nature-based solutions, or at least the concept, one could find nature-based solutions, more nature-based solution that one can imagine, actually, probably.
Okay, thank you very much. We've reached time for our today's webinar. Thank you all for your insightful questions, and a big thanks to you, Jacopo, for such an engaging presentation.
Thank you. Oh. No.
Now, I am excited to announce our next webinar. We will be having Professor Aquilea Samaras from the Democritus University of Trace, as well as Professor Patricio Winkler from the University of Valparaiso. So please don't forget to join us on April 1st at the same time through this online Zoom channel. And thank you again for participating in our webinar today and for engaging in such meaningful discussions. Finally, stay tuned for more details, and don't forget to mark your calendars, as this will be another fantastic opportunity to learn from leading experts and engage with them in meaningful discussions. Have a nice afternoon and goodbye.
Bye.